Okay, let's start with that. So, in the previous class, we learned about the control hazard. Then we also discussed about how to reduce the repeat cycles by control hazard. So first, you need to understand why control hazards are caused. So which means that you need to understand the reasons of control hazard. So why control hazard are caused? So it is because you need to understand, right? So it is because control hazards are caused by taken branch. Okay, so take means that. So actually, when we learn about the process architecture, we learn that instructions. So instructions are executed from top to bottom sequentially, which means that we just increase the PC and the PC plus 4, okay, because the PC is the address of target instruction. But when we use the branch instruction or also even the jump instruction, then the PC is updated by current PC plus target of the branch instruction, right? So which means that this is not a PC plus 4. But what's the problem? The problem is that the target of the branch instruction, also the result, which means that the condition, the result of the branch instruction, condition means the true or false of the branch instruction. The condition of the branch instruction is result late. Okay, so actually this is the main reason of the control hazard. So actually in the baseline pipeline architecture, so we learned that the branch is reserved in, and the branch instruction is in memory space, right? So it is reserved. The condition of the branch instruction is reserved late. So if the branch is taken, which means that the condition of the branch is true, then we need to change the PC as the PC plus target of the branch instruction, right? It's not PC plus 4. So the problem is that previously fetched instructions need to be flushed. So which means that these instructions need to be cancelled. So which means the instructions are cancelled. So which means the cycles are wasted. So you need to remember that because the branch instruction, the result of branch instruction is reserved late. So many clock cycles are wasted by these taken branch instruction, right? So what is the solution? What is the solution for this control hazard? If you want to increase the performance of this pipeline processor. So actually the solution is simple. So we can reduce the wasted cycles, right? And then I mentioned that these cycles are wasted because the branch instruction is reserved late. So which means not to increase the performance, but not to reduce the wasted cycles by taking branch instruction, then we need to reserve the result of the branch instruction earlier, right? So that is the solution for the control hazard. So in the previous class, because in order to reduce the wasted cycles, we added the equality check logic. So I said that we can implement this equality check logic using the comparator, so like the exclusive OR logic. But I also explained that because of this added comparator, the equality check logic, then we need to consider the new data header. It is because the data forwarding muxes are in the EX stage, but as you can see, the equality check logic is added in the ID stage. So it is not in the this feedback paths of the data forwarding paths. So we need to consider the new data handled by this new pipeline architecture. So actually, I posted the board's homework assignment on the Blackboard, so you can also check the board's homework. Actually, this board's homework assignment covers the pipeline architecture part that we learned in the classes. Actually, one of the questions includes this issue: the data handled by new branch instruction. The data handled by this equality check logic. Okay. So actually, so this is another example of the branching function. So we can use the dedicated branching unit in the EX page. So then also we can, as you can see, this branch unit is located after the data forwarding multiplexers, right? So this means that the data, the required operands can be forwarded into this branch unit. Okay. So this is another design candidate. But we can also consider the branch predictor. And then as you can see, this branch predictor is called the dynamic branch predictor. So which means dynamic means that in runtime, so steady means that the results are reserved before the instructions are executed, right? So steady means that it's fixed, before the instructions are executed. But what does dynamic mean? Dynamic means that the behavior or the result of something are detected during runtime. So which means that while the instructions are executed, the result of a branch instruction is predicted dynamically. So which means that the dynamic branch prediction. So if we use the branch prediction, then we can, before the real branch result is reserved, then we can just predict the result of the branch instruction, like the true or false of the branch instruction. So this is the predicted result. But based on the predicted result, then we can decide the result, and then we can just decide if the PC is changed to the target of the branch or not. Okay. So why do you use prediction technology? Because you can know that the prediction hit rate is high. Okay, so I explained that in the example. So if we use the iterative loop, then we know that this iterative loop includes the branching function, and then we know that when this loop is executed, then we know the branch is reserved as true many times, right? So we can easily predict the result of the branch instruction. So we can use this branch prediction. So and then I also explained that for the branch prediction, we can predict the result of branch instruction. That is the future, the future event based on the past, the previous events of the branch instruction. So we can design the 1-bit predictor. Also, we can design the 2-bit predictor. So 1-bit predictor means that we just check the one previous event of the branch instruction, and then 2-bit predictor means that So there are two bits. So this is just the saturated count, and the count, this bit values are increased if the branch is taken, and decreased if the branch instruction is not taken. Then so we can have the four different states from the 002, 11, and then if the current states are 00 or 101, and the branch instruction is predicted as the not taken, and then if the current states are 11 or 10, then branch instruction is predicted as taken. So I will explain how the result of the branch instruction is really predicted in the hardware. So I said that this 0, 0, 0, this is 1. So 0, 0, 0, 1, 1, 0, 1, 1. So these are states of the branch predictor. Then how can you use this branch predictor? So we can know that in the program code there will be many branch instructions, many different branch instructions, like the PQ or PEQ, also another PQ or PNE, blah, blah, blah. So there will be many branch instructions. Then how can we decide the stage of the prediction state for different branch instructions? So think about this. In this example, there are 3 different branch instructions. Then the behaviors of these different branch instructions are independent or dependent. It's separated or it's, so we can use the one state for this different branch instructions. So usually the behaviors of the different branch instructions are also independent, just separated, right? So these are different instructions. So like so we can use the different for loop, and then we know that the behaviors of the branch instruction, which are included in the first for loop, are different from the behavior of the branch instruction in the different for loop, right? So we can know that the behaviors of the branch instruction are different, which means that these state bits, like so we assume that the branch predictor is the 2-bit predictor. These state bits are assigned independently to the different branch instructions. Okay, so these are 2-bit predictor. So which means this 2-bit data, different 2-bit data are assigned to the different instructions, and based on the real behavior of branch instruction, then the states are changing. So for example, let us assume that the first BQ is taken. Then the state bit for this BQ is changed to the 01. And then it's taken also for this first branch instruction, then it is changed to the 10. And then next, let us assume that the second BQ is taken. So in this case, these prediction bits are changed in, changed into the 01. So I said that these state bits are independently assigned to the different branch instructions, right? So how can we implement this branch predictor? So first, how can we identify different branch instructions? How can we use? How can we identify? How can we distinguish different branch instructions? So which means how can we identify different instructions? We can use program counter, right? Different instructions have different program counter values, right? Because program counter is just pointing the instruction, the address of instruction. So using the program counter, we can identify different instructions. It's the same to the branch instruction. Using the program counter for different branch instruction, we can identify different branch instructions. So the branch predictor can be implemented like this. So this is the branch prediction buffer, and then each entry has the 2-bit value, like 0001 or also 0010, blah, blah, blah. And then these entries are indexed by program counter. Okay. So for example, so let us assume that the BQ or the program counter of this first BQ is the like the 00. Okay, it's 4. And then this is the 12 and this is 16. So we can know that, oh, now the processor is executing the first BQ by checking the program counter. If the program counter is 4, then the PC is 4, and then using this PC, then this entry is 20. And then if the branch is taken, then we can just change this value into the 01. Okay? The branch predictor works like this. So that's why so actually the branch predictor has many entries, and then these entries are indexed by program counter. But we know that the program counter is very wide, 30 width. So if we use the entire bit of this program counter, then the branch predictor buffer will have many entries, right? So the buffer has many entries, and hardware resources are also used. The large amount of hardware resources are required. So instead of using the entire bit of the program counter, we use the part of bits, okay, to identify the branch instruction, okay. And then each entry has this state bit, and then when the branch instruction is executed, then the target state bits are updated, okay. So using this branch predictor, we can predict the result of a branch instruction. Also, I mentioned that we need to know the target of the branch instruction. But I said that we can easily know the target of the branch instruction. It is because when the conditional branch instruction or jump instruction is executed, so we can calculate the target. This target of the branch instruction is calculated as the PC. This PC is the current PC for the branch instruction plus immediate. Okay. So this is the fixed value. The PC is the fixed value for the certain branch instruction, right? So we can identify different branch instruction with PC program count. Also, the immediate value is the constant value. So this is constant and this is constant. So constant plus constant is also constant number. So which means if a branch instruction is executed once, then we can figure out the target of the branch instruction. Then we can just store this target. So how the branch target buffer also works like the branch prediction buffer. So we can identify different branch instructions using the program counter, right? So there are many entries. It's a branch is this buffer. This buffer is called the branch target buffer (BTB). So this buffer has many entries, and then also these entries are indexed by part of program counter, right? And if the branch is executed, then the target is calculated, then this target is stored in the one of the entries of this branch target buffer, right? So after that, why do we use the branch predictor? Because we can expect that the branch instructions are executed repeatedly, right? Because we can use the branch instructions in the iterative loops. So once the branch instruction is executed and target is stored in the one of the entries of the branch target buffer. And if this branch, the same branch instruction, the PC is the same. If this branch, the same branch instruction is executed, then this target is read from the branch target buffer. So we can get the target of the branch instruction. Okay. So in the 5-stage pipeline architecture, so this is the instruction fetch, the instruction decoding, and then execution, and then other memory, and then write back. So branch instruction is actually located in the instruction fetch stage. Is it because we want predict the result of a branch instruction as early as possible? Also, we need to know the target of the branch instruction as early as possible. Okay, that's why the branch instruction is located in the instruction fetch stage. So which means that in the instruction fetch stage, the program counter is decided. Okay, and then with this program counter, we read the instruction memory, right? And then at the same time, with this PC, we can access the branch prediction buffer. Also, we can access the branch target buffer with the PC, the program counter. So if we just access the branch prediction buffer and branch target buffer, we can get the prediction result of the branch prediction here. So we can get the target of the branch instruction. Then what's the benefit? Oh, we can predict the result of the branch prediction as early as possible in the instruction fetch stage. Okay, so it's true or false. And then we can also get the target of the branch instruction. And then using the result of branch instruction and the target of the branch instruction, we can just update the PC the next cycle. Okay, you can just update the program counter. Okay, so that's why we use the branch predictor. So just to remember, the control hazards are also very critical for the performance of pipeline architecture. And then why? Because the result of branch instruction are determined the result late. So we want to figure out the result of a branch instruction as early as possible. But it's not possible because so because the branch need to be decoded also. So actually we need to calculate the result of the branch instruction. So we want predict because we can know that the prediction rate, the prediction hit rate will be very high. So we want predict the result of the branch instruction. So branch prediction buffer and then branch target buffer is located in the instruction text page, and then this branch prediction buffer and then branch target buffer are accessed by program counter, and we can get the predicted result and target of the branch instruction as early as possible. Okay. And the problem is that this is just the predicted result. So this is not a real result. So this is a predicted result. So this means that the prediction can be incorrect. Okay. So actually the branch is predicted incorrectly. Then we need the clock cycle will be wasted, right? Because we need to check the correctness of the branch instruction and the EX region. So if the prediction is wrong, then we need to modify the next PC of the next PC by the branch instruction. So in this case, the clock cycle will be also wasted, but because the prediction rate is prediction hit rate, so the prediction hit rate is very high, and we can reduce the wasted clock cycles using branch prediction buffer and branch target. So actually, in the pipeline architecture is actually in the modern processor, the performance of branch prediction is critical for the performance of the processor actually. Okay. Because we can observe many branch instructions in our code, and then go over these branch instructions, and actually the hit rate of the branch predictor, that is the performance of the branch prediction, is critical for the performance of the processor. Either because if the prediction is wrong, it's incorrect, then clock cycles are also wasted. Okay. So now, let's learn about the exceptions. So it's the kind of a new concept. Okay. So what are exceptions? So as you can see, the name of this event is an exception. So it's yewe in Korean. So which means that it's very rare event. Okay, so exception. So it's very rare. Okay. So then, what are the normal events in a processor? So normal events are actually instructions. So why do we use processor? Because we use a processor in order to execute instructions. So actually the instructions are normally the instructions are executed inside of a processor. Then what are exceptions? Exceptions are unexpected events, right? But what are unexpected events? It's like the overflow. So what is the overflow? So we can just add the very large number and very large number. Then what's the result? It can be 0, 0, 0, 0. It is because the bits are hardware resources. So actually the computer processors have limited hardware resources. It's a physical, it's a real hardware. And then if the very large number is added with the very large number, then overflow may occur. and the result may be 0, 0, 0. It's very small number. But this result is incorrect, right? So large number plus large number is the very large number, right? But in a computer processor, if overflow occurs, then large number plus large number generate very small number. So this is the incorrect result. So computer processor needs to detect these unexpected events because these are incorrect result. And then if a processor generates the incorrect result, then our program will work. Also, our program will work incorrectly, right? So we need to avoid this event, this case. Also, another example of the unexpected event is the divided by 0. So like the A equals 1,000, and then B equals 0, and then C equals A divided by B. And then what is the result for this C? It's not a number. We cannot calculate the result of the C, but we just handle the many data, and then for some reason, then B also can be 0, and then if some number is divided by 0, then it is the it will generate actually the computer. We cannot calculate the result of the C, right? Also, it's the same to the processor. A processor cannot generate the correct result for this equation. So this event is also the rare event because it's not a normal case. So it's similar to the fault or incorrect computation. Okay. So processor also needs to detect these unexpected events. Okay. So these unexpected events are called exceptions. So processor needs to detect exceptions when the instructions are executed. Okay. So another rare events are interrupts. So actually the exception and interrupts. So exceptions and interrupts are same rare events, the rarely happening events, but it's a little bit different. The exception is just the unexpected events. Okay, then what are interrupts? It's like some request, the kind of request or kind of some, how can I say, kind of also it's an event, okay, from I/O devices. So I/O devices mean it's input and out devices such as keyboard, mice, like this touch screen. So these are input and output devices. Then why do we use the interrupt? So a processor is running some application or program code, and then we just click the mouse buttons, or we can just click some keys of the keyboard. Okay, then the processor needs to handle these events. Okay, so if we just push the key button, then the computer processor gets the key button push event from the computer system, and then this processor needs to handle this event. So these kind of events are called the interrupt. Okay, then how can you handle these exceptions or interrupt? Exceptions and interrupts are handled by operating systems, not hardware. Okay, it is because is a rare event. Okay? It's not frequently, it doesn't frequently happen. Okay, so because this is the rare event, these exceptions and interrupts are handled by software, not hardware. Okay, so hardware does not implement some hardware resources for handling exceptions or interrupts. Hardware just detects the exception and interrupt, and then hardware returns the causes of exceptions or interrupt. So we know actually the operating system knows what kind of exceptions are detected in the hardware, right? So hardware just returns the first exceptions or interrupt, and also returns the causes, the reasons of exceptions or interrupts to the operating system. Then operating system has the software part that handles the exceptions or interrupts. So this is the software part, is the kind of instructions, right? The software, right? Operating system includes the software part that handles the exception or interrupt, like the program code. Then, how exceptions are handled in the processor. So hardware detects the exception, and operating system has the required code for handling exceptions. So exceptions are detected, then hardware changes the program counter to the first instruction of the exception handler. So this software is called the exception handler. Okay. The hardware changed the program counter to the first line of the exception handler. So what does it mean? The current programs are just stopped, temporarily stopped, and then PC, the program counter is changed to the first line of the exception handler. So which means that these first instructions of the exception handler will be executed by hardware. Okay, and then these instructions are executed and then return to the previous instruction, or just to stop the programs. So for example, so if the divided by 0 is detected, then you can just stop our program, right? Then so then divided by 0 is detected in the execution stage. Then the processor changes the PC to the exception handler for divided by 0, and then these codes are executed for handling divided by 0. And then it can return to the original instruction, or the programs can be terminated. Okay. So what is required? So I explained how to handle exceptions. So what is required? So first, how do you need to detect the exception? Also, how to need to return the causes of exception, and program counter is changing to the first line of the exception handler. It's very similar to the jump. Okay, but jump instruction is not executed in this case. The hardware just changed the program counter to the first line of the exception handler. Okay, and then it returns to the original location, original instruction. Okay. So these operations need to be supported by hardware. Okay. Understand? So actually, the exceptions is a rare event. So it's not saying to the normal operation of the, so it's not a normal operation of the process. But the exceptions also need to be supported by hardware, even though the exception handlers are provided by operating system, but the hardware also needs to support the exception, the detection, and then also the change of a program counter to the exception handlers. Okay. So in the risk five has some special registers for the SCPC. Okay, so this SCPC is called the supervisor exception program counter. So in this SCPC register, the current PC of the instruction is stored. Okay. So I said that the exception is detected in the processor and its PC is stored in the SCPC, and then the exception handler is called by a processor. Okay. Then exception handler execute the processor execute the instruction in this exception handler, and then we can return to the original instruction. Okay. Then we require the program counter if we want return to the original instruction, right? That's why the SCPC is required. The risk file has the SCPC register, and then the SCPC register, the current program counter is stored. Also, risk 5 has the SCOSE. So this SCOSE register is called the supervisor exception code register. So I mentioned that the hardware needs to return the codes of exceptions, okay? Like the overflow or divide by 0. So the exception, a certain kind of exceptions is detected by hardware, then the hardware just updates the SCOSE register. So, and then each bit of the SCOSE register is mapped to the default codes of exception. Then the hardware returns this SCOSE to the operating system. And then jump to handler. So based on the codes of exception, then the hardware decide which exception handler will be called. Okay, but this information is also stored in the processor. When the operating system is launched, and this information is updated in the processor, and then the exception handler, the required exception handler is called by the processor. Okay, that's how the exception is handled in a processor. Okay, so in order to support the exceptions, then we require the new hardware component like the SCOSE and then SCPC. So here, and then as I mentioned, when the exception is detected, then we need to call the corresponding exception handler. So this is just the hardware has the program counter, the address for the exception handler, and this program counter, it can be selected by this multiplexer, and then it is updated to the program counter register of this file. Okay, so this is the example of handling exceptions in the pipeline processor. Okay, so exception. I explained how to handle exceptions in the hardware. Okay, so, and then the exception is the another form of the control hazard. Okay, so when an exception is detected, then we need to also cancel the text instructions, right? So I will explain how the instructions are handled when an exception are detected in hardware. So this is the example. So let us assume that the web function is detected for this add instruction. Okay. So this add instruction performs the add x1, x2, x1. Okay. But a certain unexpected events such as divide by zero or some other events such as overflow. Let us assume that these events, one of these events is detected in the hardware. So it is because this is just a malfunction, and then let us assume that this event is detected when this instruction is in the EX stage. Okay, it's detected by ALU, for example. So what should we do? So first, the exception is detected. Okay. Then, as I mentioned, a hardware stores the PC of the this instruction, the add instruction. Also, hardware stores updates the COSE register for the some causes for logging causes of this exception. But this is the pipeline processor. Okay, so pipeline processor. So it's instruction fetch, ID, EX, and then memory write back stations. And then let us assume that currently the add instruction is in the EX stage, and then when this add instruction is in the EX stage, the exception is detected for this add instruction. Right. But we know this is the pipeline processor, and the pipeline processor also includes the other instructions in the different stages, right? So there can be previous instructions like the P1 and P2, and then also this pipeline processor also includes the next instructions like N1 and N2. Okay. So there are also other instructions inside of stages of this pipeline processor. So what should we do? And then exceptions are detected. This is the just malfunction. So because the exception is detected, then we can expect that this instruction will generate incorrect result, right? Right. So if this instruction is executed, and then this instruction will generate incorrect result. So what do we do? We need to cancel this instruction. And then this event, the exception event, need to be handled by exception handler. But before jumping to the exception handler, then processor just cancel the execution of this instruction. So cancel means that just it becomes the bubble, right? And then how about the previous instruction? Is this instruction correct or not? So is this instruction correct or not? So exception is detected for this add instruction, but we know P1 and P2 are correct instructions, right? So which means processor needs to complete executions of P1 and P2. Understand? Because these instructions are correct instructions, not the exception is just caused by this add instruction. So processor needs to complete the execution of P1 and P2. So which means the P2 is in the write back state. So which means that the P2 should be the result of P2 should be written back to the register file. Also, it's the same to the P1. The P1 is memory stage, and then in the next clock, the P1 will be propagated to the write back stage. And then the result of P1 also need to be written back to the register file. Okay, you understand? The processor needs to complete the correct instruction. Then how about the N1 and N2? So in this example, N1 is the next instruction, the N2 is the another next instruction. So what should we do? So actually, I said that the instructions are executed from top to bottom, and then I don't know, but some errors are detected for a certain instruction. Then how about the next instruction? So there can be any data dependencies, right? So we just write the code like A equals 1, B equals 2, and C equals A plus B. So there can be any dependencies. Also, the execution of next instructions are also influenced by former instruction. Then the exception is detected for this add instruction. So which means that if this instruction is incorrect, then we don't know the result of the next instruction, but we can expect that because of this add instruction, the result of next instruction can be also incorrect. So probably. Okay. So what should we do? We need to cancel also the next instructions. So in a pipeline processor, so the exception is detected only for add instruction, but following instructions like add 1 and N2 also need to be cancelled. So flushed. So it becomes the bubble. So you need to remember. So first exception is detected. Then the pipeline architecture, previous pipeline architecture need to complete the execution of previous instructions. Okay. And then current instruction, the exception is detected for this current instruction. The execution of current instruction is cancelled. Also, the executions of next instructions are also cancelled. Okay. So in this example, processor flushes these 3 instructions. Okay. So it's very similar to the taken branch, right? When the branch is taken, so when the branch is taken, then we need to cancel the following instructions in the pipeline stages, right? It's the same. So, exception is detected. Then the following instructions are also flushed and jump to the exception handler code. That's the required operation for handling exceptions in a hardware. Okay, so this is the example. So this is the code, and then as you can see, is the program counter of these instructions, and then let us assume that the exception is detected for add instruction, and then this is the program counter of the exception handler, So exception is detected for this add instruction when this add instruction is in the EX stage. Okay, so which means in the pipeline stages, this pipeline state processor includes these 5 instructions. But as I mentioned, this pipeline process needs to complete these instructions and an OR instruction, and then these instructions need to be flushed. Okay, and then because the exception is detected, and you need to jump to the first line of the exception handler. The program counter is the 1C090000. Okay, the processor needs to support this operation. Okay, so this is the example. So as you can see, the add instruction is in the EX stage, and then OR is here, and AND is here. The solve is in the idle stage, and then instruction fetch stage. So exception is detected for this add instruction. So first, we need to store the PC of this add instruction in the SCPC, right? So you can find the SCPC here. Also, the causes of exception need to be logged in the SCOSE. Okay, right? So exception is detected, and then in the next cycle, this is the next cycle. So processor needs to cancel add instruction, sub instruction, and then this load instruction. So in the next cycle, because the load instruction is canceled, we can find bubble in the idle stage. So this is the next cycle. So you can find another bubble in the EX stage. So this is the bubble from sub instruction, right? So you can find another bubble. So this bubble is from add instruction. So add instruction, and then the following 2 next instructions are also cancelled. So it becomes the bubble. And you can find store instruction. So what is this store instruction? This store instruction is the first instruction of the exception handling. Okay. So a processor jumps to the exception handler, and then processor just fetch the instructions for its instructions of the target exception handler. But as you can see, the OR instruction here. So what is this OR instruction? The OR instruction was in the memory stage, right? So in the next cycle, the OR instruction is just propagate to the right stage. So processor can complete the execution of OR instruction. So the result of OR instruction is stored in the register form. And then, so in this example, there is no, you cannot find any future instruction after the exception handler is executed. But so let us assume that this exception is the recoverable exception. So which means that the result by this exception is handled by exception handler, and then the result can be recovered. Okay. Then we need to continue the add instruction, the original program. Okay. So there are 2 kinds of exceptions. The first one is that the exception can be recovered can except the program, actually the programs can be recovered from the exception, but and then if the program is not cannot be recovered from the exception, then program need to be terminated. So let us assume that the program is instruction, actually this program can be recovered from the exception. And what should we do? So all instructions in the exception handler are executed. And then we can, so this program can be recovered from the exception. So we know the exception is caused by add instruction, and then add instruction is cancelled. So and then after the instructions in exception handler are executed, and processor resume the execution of add instruction. Okay, so this is the recoverable exception. The program can be recovered from the exception. So actually the exception is detected for this add instruction. So add instruction is cancelled, but processor need to actually, this is the program, and then in order to execute the instruction in this program correctly, then processor need to execute all instructions, right? So when the exception is detected, the add instruction is cancelled. And then if the processor is recovered from the detected exception, then processor resume the execution of this add instruction. The processor can read the PC, the SPC from the SEPC, because SEPC told the program count of the add instruction. You understand? That's why the SEPC also stores the program count of the target instruction where the exception is detected. Okay. So that's how the exceptions are handled in the processor. Okay. And then another some complex situations, the multiple exceptions. So what does that mean? So actually, you can find the question about the multiple exceptions in the homework assignment. So actually, the last question has some situation about the multiple exceptions. So what multiple exception means that? So actually, processor has the multiple stages like instruction fetch, instruction decoding, and the execution, and memory, and write back. So there are many instructions. Actually, this processor is executing 5 instructions, like instruction 1, 2, 3, 4, 5. But exceptions can be detected any stage of pipelines. So for example, the exceptions can be detected in the ID stage because the undefined instruction is fetched from the instruction memory. Then processor cannot execute this instruction because this is the undefined instruction. Also, as we mentioned, the exceptions can be detected in the EX stage. Also, the exceptions can be detected in the memory stage. What does that mean? There are many kinds of exceptions, and then the exceptions can be detected in any stages of pipelines, which means it's a very, very rare case, but multiple exceptions are detected in the pipeline processor. So for example, exception is detected for this instruction 4, and so at the same time, the exception can be detected for the instruction number 2 at the same time. Well, it can be possible. Then what should we do? So in this case, the exceptions are detected for instruction 4 and 2. The first question is that which exception need to be handled first? 4, right? Right. So it's a rule. In a processor, instructions are executed from top to bottom sequentially. It's the same for the exception. So even though it's the same time in the real world, but if we see the order of instructions in this pipeline processor, then we can know that instruction 4 is the forward instruction, right? So which means we need to first handle the exception for the instruction 4 because this is the forward instruction, and then we need to handle the exception of by instruction number 2. Okay. So it means, so we learned how to handle exceptions in a processor. So let us assume that the exceptions are detected for instruction 4 and 2 at the same time, but in this case, the exception by instruction 4 has higher priority. So SEPC stores the PC of instruction number 4. So as cause logs the causes of exception for instruction by instruction number 4. And if we see that this pipeline, then instruction number 5 is the former instruction, and then 1, 2, 3 are next instruction. Same rule can be applied, which means this processor cancels these instructions. Because the exception by this instruction 4 has the higher priority. Then what will happen for the exception by instruction number 2? It's just ignored, okay? But it's okay because if this exception is the recoverable exception, then processor will also execute the instruction number 4 again, so which means that instruction number 3, 2, 1 will be also executed. So in this case, the exception is already handled for this for instruction number 4. Then exception will be detected for instruction number 2 again. Okay, you understand? The first exception for this former instruction is handled, and if this exception is the recoverable exception, then this processor will resume the execution of instructions from instruction number 4. But we know that the instructions are sequentially executed, then instruction number 2 will be also executed when the program is resumed this processor. Okay, understand? So after that, after the exception by instruction number 4 is handled, then exception by number 2 will be also handled. Okay, because the program will be resumed from the instruction number 4. So actually, this kind of exception handling operation is called the precise exceptions. which means the exceptions are handled in the order of instruction. Okay. But so actually, but modern processor has a very complex pipeline architecture. So actually, in the undergraduate course, we are learning about the in-order processor, so which means the instructions are executed in order. So which means the instructions are executed from top to bottom. So this is the in-order processor, but the problem is that the performance is not good. Okay, so which means actually the modern computer systems use the out of order processors. So actually our desktop, laptop, also even our smartphone use the out of order processors, and then which means the instructions can be executed out of order. So actually, the pipeline architecture, so in the instructions are executed in order. So it means that 5 is executed, 4 is executed, and blah blah blah. But in the modern processors, this order can be changed like the instruction 1 is executed first, and then 3 is executed, and then 4 is executed, and then 2 is executed. The order can be changed. So in this case, as I mentioned, the exceptions also need to be handled in order. So it means that the exceptions need to be handled in the order of instructions. But for some out of order processors, this operation is very difficult. So some processors do not support this ordered exception handling. So which means that this exception handling is called the precise exceptions, but some processors do not support precise exceptions. Okay, because this is a difficult operation. So it requires the very complex hardware. Okay, but precise exception is also very important, because if the exception is detected, then we need to check the code of the exception, and so we need to fix the exception in our code. So, but precise exception in the modern processor requires the very complex hardware. So sometimes some processors do not support precise exception. But just remember that in the processor, the instructions are executed from top to bottom, which means the exceptions need to be also handled from the order of instruction from top to bottom. And this exception handling mechanism is called the precise exception. Okay. So even though this is the rare case, but in order to support the rare cases, hardware maybe so actually, this is the end of the pipeline process architecture for the undergraduate course. So actually, this is the very important part of this course. We hope we can understand the basic fundamental rule of this pipeline architecture. Also, we learn corner cases are difficult. Actually, the fundamental idea is very simple. Just to apply the pipeline idea. So we know that this pipeline idea is very simple, right? But in order to execute instruction correctly, also in order to increase the performance, then we need the pipeline architecture need to support the data forwarding and hazard detection. So in order to reduce the weight of the current pipeline by control hazard, then we also learned about many techniques like branch prediction or branch target control. So the problem is in order to increase the performance, the architecture can be more complex. Also, exception. In order to support precise exception, the hardware architecture is also very complex. Okay, becomes complex. So actually, in order to handle the corner cases, the hardware becomes more complex. So that's actually it's the same to the real world. Actually, the rule, the basic rules are very simple, but in order to handle the corner cases, our society our becomes very complex, right? And then it's a real world. Okay, actually, hardware learns in the real world. Okay. Okay. So I will stop here. Any questions? So in the next class, we will move on memory hierarchy. Okay, chapter 5. Okay. So thank you for your attention and see you in the next class. 감사합니다.